Okay, so first of all, I, of course, want to thank the organizers for giving me this opportunity. I love Bonn. I've been here in September. It's very nice to be back. Okay, so I have to admit that my title is a little bit random, so I will definitely talk about all of those things. But generally, what I want to talk about is a uniform distribution theory and its quantitative version, the discrepancy theory, and its relation with the Fourier analysis, and in particular with lacunary Fourier series and Riesz products. The uniform distribution theory originated in the work of Hermann Weyl in 1916. So I'll start right with the definition. So if you take a sequence in the unit interval, it's called uniformly distributed if asymptotically the proportion of points that fall into a given interval equals the length of that interval for all intervals. So every interval gets a fair portion of the points. Okay. Well, you could rewrite this definition in the following way. If you take the characteristic function of the interval, on the left-hand side, you would have 1 over n times the sum 1 to n, the characteristic function of the interval evaluated at xn, and that has to converge to the integral from 0 to 1 of the characteristic function of the interval. So discrete sums converge to the integrals. Now, from this, it's trivial to extend this to all step functions and then to all continuous functions. And Weyl's criterion that he formulated in that work is just an observation that due to Weierstrass theorem, you can now test this condition just on the complex exponentials, on trigonometric polynomials. Complex exponentials are dense. So this is Weyl's criterion, essentially. It says that you want the sequence is uniformly distributed if for every k right here, this limit is 0. Okay, and that's precisely this condition, but with this function instead of the characteristic function of the interval. It has a very nice geometric interpretation also. So by computing this average here, what you're doing is you're putting your points on a circle, and you're taking the center of mass of these points on the circle. Okay. So, and if your sequence is uniformly distributed, you want that center of mass to be close to 0. But you can still have 0 if, say, the points are all concentrated in the vertices of a regular polygon, say in a square. But we take this for all dilations. We take all dilations k, and that takes care of such cases. Okay. So this is a very important criterion, and it already shows you that harmonic analysis comes in right away. So right away you have exponential sums. It has numerous applications. Some of the most immediate are the following. First of all, if you take the Kronecker sequence, fractional part of n theta, where theta is irrational, that is uniformly distributed. It's very easy to check this condition. This would just be a geometric sequence. And the second, which is just a little bit harder. Now, if you take any subsequence of integers, and you consider this sequence, fractional part nk theta, this is uniformly distributed for almost all theta. Okay, so that's also quite easy to show. So these are the first two consequences of Weyl's criterion. Okay. Well, you can ask the question how you can quantify this uniform distribution. Well, here you can use what's called discrepancy. Well, that's essentially the error in the definition from the previous slide. So this was the definition. If you take the error here, well, I do not normalize it. I multiply it by n. Okay. So that's the discrepancy. You look at the maximal error in that convergence, and you take the supremum over all intervals. Well, it's quite easy, again, to see that your sequence is uniformly distributed if and only if the discrepancy divided by n, normalized discrepancy, goes to 0, and then goes to infinity. Okay, now this is the result from the first slide. We know that for any subsequence, this sequence is uniformly distributed almost everywhere for almost all theta. Now the question is, can you get quantitative bounds? And here the story gets already quite interesting, and again, Fourier analysis comes in a very interesting way. So there is a result due to Baker that for any subsequence, you have this bound. For almost all theta, the discrepancy behaves as square root of n times log to the power 3/2 plus epsilon. Okay, and well, this should be related somehow to the exponential sums due to Weyl's criterion. So, well, first of all, it's 1/2 here should be is the best possible. You cannot do better than 1/2. That was proved by Berkes and Philipp. Okay, well, if you just take the exponential sums like this, you can actually prove the result for exponential sums with power 1/2 here. Okay, so and why I mention that is because the proof is very peculiar. The proof uses Carlson's theorem about convergence of Fourier series. So, and well, Carlson's theorem says that you have this weak type 2-2 for the maximal operator. And you only need it in a very, very simple case. You need it for a function like this. Okay? But so far, no simplifications are known. You cannot avoid using it. Well, once you have it, then the proof only takes a few lines. Basically, you choose the parameters and use the Borel-Cantelli lemma. So you just use Carlson's theorem as a black box. But once again, there are no ways to avoid it, no known ways to avoid it. I find it quite amazing, even though the function that you're dealing with is very simple. Okay, well now, okay, so basically this is what you do, and then use Borel-Cantelli. Okay, let me skip that. Okay, well, there is a way to relate exponential sums and discrepancy. That's the famous Erdős-Turan inequality, so I've stated it here. It holds for all natural numbers m. So, and typically what one does is you apply it and then optimize in m. Okay. In many situations, you would actually choose m roughly of the same order as n, so that the first term is gone, although not always. But typically, because of this term 1/h here, you get an extra logarithm from the Erdős-Turan inequality. So it's a folklore statement that you don't get optimal bounds. For example, if you choose nice irrational numbers here in the Kronecker sequence, you are supposed to get log n to the first power, but instead you get log squared if you run the Erdős-Turan argument. Okay, and by the way, on the previous slide, so this difference of 1 log in these two results comes precisely from using the Erdős-Turan inequality. That's why you get an extra log here. Okay, so now van der Korput in the 30s asked whether a discrepancy can stay small. Basically, if you can you find a sequence so that this quantity stays bounded as n goes to infinity? And he already kind of suspected that the answer is no. In the paper, he says, I don't know of any sequences for which this would be true. And then in 1945, Van Ardiner and Fest, in fact, proved that that's true, that this can never stay bounded. And then Ross gave a much sharper quantitative bounds. He also transfer the problem to a different setting, and that's the setting that I will talk about. So basically, there's a following equivalence. You can have certain lower bounds for the discrepancy which hold infinitely often in n. That's equivalent to proving lower bounds for finite point sets. So here we had infinite sequences in the one-dimensional interval, and here we have finite point sets in the two-dimensional square. And here you want this to hold for any sequence. This is a pretty, for any point distribution. This is a fairly simple equivalence. Basically, heuristically, you can think about this extra dimension here as coming from the index here. So the index of the sequence is an extra dimension that you use here. Increases, some increase in function. Actually, I think to be precise, you need to put some conditions on how fast it increases, but roughly any reasonable increase in function. Okay, so this is the situation that I will discuss from now on. So you consider the unit square, you consider some distribution of n points in the unit square, and you look at the discrepancy function. So you look at axis parallel rectangles with one of the angles anchored at the origin, and you take the difference. How many points actually fall into the rectangle minus n times the area or the volume, so minus the expected number of points that you would like to see if the distribution were truly uniform. Okay. This comes up not just in number theory, not just in uniform distribution. It comes up very naturally in approximation theory, with respect to numerical integration. So if you have a cubature formula with equal weights, its error can be estimated by a product of two things, and one of them is precisely the extremal discrepancy, the maximal discrepancy, the L infinity norm of the discrepancy function. And the part that depends on the function is the so-called Hardy-Krause variation. It's a natural extension of the one-dimensional notion of variation to the multi-parameter case. And you can think of it, say if the function is nice, in particular if it's given as the integral of some kernel, you can think about the variation as the L1 norm of the mixed derivative. Okay. So in that way, you can see that this inequality is essentially duality relation. So you can prove some other inequalities of this type where you would, instead of the L infinity norm, you would use other norms. So other norms of the discrepancy function are also interesting from the point of view of these applications. Okay, so now the question is how do you quantify the negative answer to Van der Corput's question? So how do you quantitatively show that no point distribution can be too uniform? Okay, so if you look at the LP norms for P strictly between 1 and infinity, pretty much everything is known nowadays in all dimensions. Okay, it's for P equals 2, this was proved by Ross, that you have this lower bound, d minus 1 divided by log to the power of d minus 1 divided by 2. So for any point distribution, the discrepancy, the LP discrepancy will be at least as big. So this was extended to all P's strictly between 1 and infinity by Schmidt more than 20 years later, although using modern harmonic analysis, using dyadic Littlewood Paley theory, you could extend that in essentially one line, or 2 lines maybe. Okay, so, and this is known to be sharp. There is a lot of different examples. There was this whole series of examples that shows that in all dimensions, for all values of P, this result is sharp. That is, you can construct point distributions which achieve this order of LP discrepancy. Okay, what is the main idea of that proof? Well, the main idea is the following. So this goes back to the 50s to the work of Klaus Roth. You take the discrepancy function. So here again, we use analysis. You expand it in wavelet basis, in particular, in the multi-parameter wavelet basis. In particular, you use just the regular Haar basis. There are some little details. So the Haar functions that I use, first of all, these are multi-parameter Haar, so they're on rectangles, not squares. And they're normalized in L infinity, not L2. That's just for historic reasons. It became convention. So they look like this. So these are dyadic rectangles, and the Haar functions look like this. Because of the normalization, you have this weird thing. Okay, and the main idea was that most of the information about the function is encoded in the part of the expansion which corresponds to rectangles with fixed volume, which is roughly 1 over the number of points. Okay, so this idea could be explained heuristically. Well, if the distribution is really nice, then here each rectangle with this size would have roughly 1 point per rectangle. Also, you can think if the rectangle is too large, then there is too much cancellation and it doesn't really carry too much information about the discrepancy. Well, think about the whole square, the discrepancy is 0. If the rectangle is too small, then with huge probability it will miss and not contain any points. So really, again, it would not carry any information about the distribution. So most of the information is concentrated in these intermediate scales. Okay. So that's at least the way I see it. That's the heuristic explanation of this idea. And the idea is actually not very uncommon. So ideas like this are used in approximation theory very often. They're known as hyperbolic cross approximations. So here you use rectangles of fixed volume. That means the product of the frequencies is roughly fixed. So that means frequencies live in a hyperbolic cross. Okay. Yeah, you can view it that way too. Yeah. So okay, then once you have this idea at hand, well, then you just apply the well, essentially Bessel inequality. Well, you apply the Pythagorean theorem. Essentially, all you need to know is that the projection of the discrepancy, the Haar coefficients, are large for many R's, for some fixed portion of R's. Well, that you can achieve, and the parameter d minus 1 here comes out very naturally in the following sense. If you have this condition, that the product, that the volume is fixed, then, well, think about the rectangles. You can choose the first d minus 1 sides more or less freely, and the last side is fixed. So that means that you really have d minus 1 free parameters. Okay, so this power of d minus 1 here is essentially the number of free parameters, and the 2 in the denominator is the square root from the Pythagorean theorem. So that's essentially it. That's the idea. Okay, and you could use Littlewood-Paley theory instead of Bessel's inequality here to obtain the same results for LP between 1 and infinity. Okay. All right, so now what happens in the most interesting case? The most interesting case is the L infinity norm. That's the extremal discrepancy, the maximal error. Okay, well, the conjecture, and I'm being intentionally a little bit vague about the conjecture for now, is that it should be much larger than the LP estimate. And again, the idea, heuristically, you can explain it in the following way. If the distribution of points is really nice, then in a lot of points, in a lot of places, discrepancy should be small. It should be large only only rarely. So that's a highly localized function. It will be small at most part and large in small areas. So, well, then if it's localized, then the L infinity norm should be much larger than the average norm. The extremal norm is much larger than the average. And there are at least two quantitative conjectures. Well, it's in dimension 2, everything's known. It's log n. Okay. And the L2 norm would have been square root of log. So there is a difference. And this is known to be sharp. There are distributions with discrepancy of the order log n to the first. Okay, I just want to briefly show some examples. In this whole theory, unfortunately, up to now, and some people would probably throw rocks at me for saying that, but unfortunately, there are just two types of examples. One is, I would say, digital. So that's this in 2 dimensions is just the Vender-Corput set. It's constructed in the following way. You take all binary fractions of length n for the x coordinate, and you flip them in the y coordinate. So roughly now, when you change the x coordinate a little bit, the y coordinate changes a lot. That's why this set is very well spread out on the unit square. The important property is that every dyadic rectangle of area 1/2 to the n has precisely 1 point in it. It's very easy to see. And that's why from there it's quite easy to get this statement. Another example is number theoretic, and it deals with Kronecker sequences that I mentioned. So if you take alpha to be an irrational number, say quadratic irrational, for example, or anything, a badly approximable number, then you also have this discrepancy bound. Okay, just for comparison, random sets behave much worse, discrepancies of the order square root of n. Okay, well, so what happens with the L infinity norm? What happens in higher dimensions? You can extend, in particular, you can extend the Vender-Corput construction to higher dimensions to get discrepancy of the order log n to the power d minus 1. Okay, and that is, in terms of the order, that is the best known up to date. And that leads to one of the conjectures. So there is a conjecture that that's actually sharp. And there is another conjecture which says that this should be the right order. Okay, and for some reasons that hopefully will become clear, I believe this conjecture more. And well, for d equals 1, they both give you the same thing. Sorry, for d equals 2. Yeah, sorry. Yeah. For d equals 1, actually this one gives you the right thing, but somehow d equals 1 for fixed point sets is not an interesting case. So you can argue that. Again, so it's not clear what is correct. What is known as a result of myself with Michael Lacey and Emran Vagarshakyan a few years back is that you can beat the LP bound. So this would be just the LP bound. You can beat it by a little bit, dimensions. Okay. We also looked at what happens in spaces near L infinity. So in particular, we looked at BMO, and here BMO, by BMO I mean the Chang-Pfefferman dyadic product BMO. Let me not get into the details, but the interesting thing is that the BMO norm behaves like the LP norm and not like L infinity in this case. So the estimates in two dimensions are of the order square root of log and not log. And this can also be, it seems that this can be extended to higher dimensions. So we recently did this with Alev Merhassan, but we didn't write it down yet. So that's why I don't quote it in the slides. We also looked at the exponential spaces. And the results that we got in that case are some sort of a smooth interpolation between the LP and the L infinity estimates. So here alpha is between 2 and infinity. If alpha is 2, you're in the sub-Gaussian case, you get square root of log. You get the same as the LP bound. If alpha goes to infinity, you approach the L infinity bound, log n to the first power. Yeah, there is a lot of work also on discrepancy in other function spaces, so I just list some of it here. Okay, let me move on to the other endpoint of the scale, so of the LP scale. So what happens at L1? In 2 dimensions, it's known that you get the same lower bound as in LPs, square root of log. And this was proved by Halas in 1981. His proof also implies that the same bound holds in higher dimensions. And unfortunately, we don't know anything else about about the L1 norm in higher dimensions. That is, we don't even know that the bound grows with the dimension. The conjecture is that the L1 bound is of the same type as the LP bounds. Okay. However, what's known is just some bounds in the L log L spaces and in HP for p between 0 and 1. Well, recently, in 2013, Amir Khanyan, myself, and Michael Lacey, we proved a series of results which we called the dichotomy results for the L1 discrepancy. The dichotomy here is in the sense that we cannot prove the conjecture, we cannot prove the L1 norm is large, but we can prove that one of the two things happens. Either the L1 norm is large or some other norm is very large. Okay. In other words, if some other norm is small, then the L1 norm has to be large. So here is a sampler of results we actually proved even more. I will just comment on the first one really quickly because the first one is actually trivial. In the first one, you just apply Hölder inequality like this. Well, you say, you write that the L2 norm is bounded by the L1 norm times the L4 norm or something, or use some other. And now say you know that this is big, this is Ross's theorem. Okay? And if you additionally know that this is small, then this has to be big. And actually all the other results, even though the proofs are much harder, all the other results are of the same spirit, in a sense. Okay. So, but unfortunately, still nothing can be said about the conjecture itself. Okay, well, now I want to relate this problem to a problem which is purely from harmonic analysis, purely about product wavelets. So this is a so-called small-ball conjecture, the small-ball inequality. And probably you can see already that it must be related because, well, sums like this already appeared when I talked about Ross's method. So we dealt precisely with linear combinations of Haar functions over rectangles with fixed volume. So this is the conjecture. The point of the conjecture, the important point is this exponent right here. If I replaced it by d minus 1 over 2, this would be almost trivial. You could just prove it for the L2 norm here. Again, this would come from the fact that d minus 1 is the number of free parameters. Okay. This is known in 2 dimensions. It was proved by Talleyrand first and then subsequently by Temlakov with a different proof. Okay, you can show that if true, this would be sharp. For this, you just take alphas to be the random choices of signs. Okay. And it comes from problems in approximation theory and probability. So Talleyrand was interested in it from the probability point of view, Temlakov from approximation. But it also is related to discrepancy, but in a slightly mysterious way, so we don't understand it completely. So if you look at both conjectures, the small-ball conjecture and the discrepancy conjecture that I said I believe more, in both of them you gain a square root over the L2 estimate. So here with d minus 1 over 2, this would be the L2 estimate. Okay, here with d minus 1 over 2, that would be the L2 estimate. Also, they look even more alike if you restrict your attention to the coefficients being just plus minus 1s, then they really look almost the same. And we know that this is sharp. That leads us to the belief that this may be sharp for a discrepancy function. However, we don't know if there exists any direct relation between the two theorems. So here, this summarizes everything that's known and everything that's conjectured, or at least the conjecture that we believe in, go in parallel, in complete parallel, for the small-ball inequality and the discrepancy estimates. But again, we don't have any direct relation. Here, this picture summarizes the relations between the different problems. The dashed line means that there is a vague heuristic relation between two things. The solid lines means that there is actually a solid relation. So there are two problems. This is the problem from approximation theory. It's the metric entropy of class of functions with mixed derivative bounded in L2. And this is the probability of small deviations for the Brownian sheet. Actually, you can put more dashed lines on this diagram. And I don't have time to talk about them right now, but you can put a dashed line here also, for example, because the discrepancy function of a random sequence of points converges in many different senses to the Brownian sheet. Okay, now I want to show the proof. Now I actually get to Riesz products. That was the third part of my title. I want to show the proof of the two-dimensional small-ball inequality. This proof is, I believe that it's a proof from the book. If the book exists, well, most proofs that are claimed to be from the book are usually from combinatorics. So well, this one is from analysis, and I think it is. I truly believe that this should be in the book. Okay, so you want to show a lower bound for the L infinity norm of this guy. Okay, so we construct a test function in the following way. First, okay, we construct auxiliary functions like this. So here, notice the volume is fixed. We're in 2 dimensions. We also fix the length of one side. So that means we completely fix the shape of the rectangle. So, well, for a moment, forget about the sign right here. If this was not here, this would be a Rademacher function. This would be a perfect alteration of signs. So here, what we do is we flip some of the signs. Basically, we want, when we multiply, we want to get the absolute value. Okay. So now I construct a Riesz product. like this. So what can I tell about this function psi? First of all, it's non-negative, just because all these guys are plus or minus 1. So this is 0 or 2, so the product is non-negative. Second, its integral is 1. Okay, that can be seen in the following way. Expand the product. Okay. The leading term is 1, and all the other terms, actually, you can see that they will be Haar functions again. Okay, and they have integral 0. Okay. And now, that tells you that the L1 norm is 1. So that's good as a test function for an L-infinity estimate. Okay, so you just run this. Now here the same thing would happen. When you expand the product, the only time you get something with non-zero integral is when a Haar function from here hits a Haar function in here. And there you get precisely this right-hand side. Okay, that's precisely the right-hand side that you're in. Okay, so this is due to Temlakov. But the idea, actually, maybe some of you may recognize the idea from the theorem that you may have seen in a basic Fourier analysis class. So if you think back into the history when the Riesz products first appeared and why, that was in relation to lacunary Fourier series. Okay, so in particular, they were used to prove Sedon's theorem. And the similarity is very apparent. So this is a small ball inequality in 2 dimensions. And this is Sedon's theorem about lacunary Fourier series. So basically, both of them deal with bound in the L-infinity norm of a certain sum from below by the sum of the absolute values of the coefficients. Okay. So here, this says essentially that if a bounded periodic function has lacunary Fourier series, then the Fourier series converges absolutely. Okay. And the way this theorem is proved is precisely by more or less the same Riesz product. Okay. Well, you have to assume, so it's more technical here. You have to assume first that the lacunarity constant is large. You have to work a little bit more here. That case turns out to be very clean. But the idea is exactly the same. So it's a twin proof. And for a discrepancy function, almost the same proof works. Again, it becomes more technical because you also need to take care of the higher order terms and things like that. But the idea is, again, identical. And initially, it was done with a more hands-on approach. But the Riesz product proof was given by Halas in '81. Okay, and you can see, again, that there is a obvious similarity between the behavior of the discrepancy function and the behavior of lacunary Fourier series. By the way, there is another Sedon's theorem for about the L1 norm of the lacunary Fourier series, well, which essentially says that all the LP norms of lacunary Fourier series are equivalent. So essentially, this is what this theorem says. The way it was proved is also by a Riesz product, by a Riesz product of this type. And Halas did the same thing for the L1 norm of the discrepancy function. And I strongly believe that you probably read Sedon's papers or a book on basic Fourier analysis before writing this paper. It's a very nice paper, and it's really very closely mirrors these ideas. It also raises some interesting questions. For example, here it is known that it is now known that this bound can be proved as a consequence of the L-infinity bound. It can be derived from the L-infinity bound. The question is, can you do the same thing here? This would be very interesting to know. The same methods do not work. Here you use a certain randomization of coefficients. But maybe some other method would work, and that would shed a lot of light on the behavior of the discrepancy function. Okay, now I just talk for about one slide about some special subsequences of integers. So there are two pretty well-known classes of subsequences. That the Sedon sets are essentially the subsequences such that Sedon's theorem works. Okay, such that you have this, and such that if the spectrum of the function is supported in that sequence, then you have Sedon's theorem. Okay. And this has been studied very heavily. And but still, there is no there is no characterization. There is no characterization of Sidon sets. And there is also another closely related but a little less well-known class of sets that's a spectra of uniform convergence. Okay, so if for Sidon sets in the definition you assume that the Fourier series converges absolutely, here you assume that the Fourier series converges uniformly, okay, for every continuous function with spectrum in this sequence. Well, and of course, being a Sidon set implies that it's a set of a spectrum of uniform convergence. It doesn't work. They're not equivalent. So there are spectra of uniform convergence which are not Sidon sets. You can construct spectra of uniform convergence which have density which behaves like log n to any integer power, and it's known from a theorem due to Stechkin, I think from the 20s, that for Sidon, for a set to be Sidon, it has to have density which behaves no worse than log n to the first power. So, so there are more sets that are spectra of uniform convergence than there are Sidon sets. And there is a conjecture about the spectra of uniform convergence due to Askolkov that the property of not being a spectrum of uniform convergence is related to uniform distribution. It's related to the following property, that for each irrational theta, this sequence, the subsequence of the Kronecker sequence, is uniformly distributed. I put this in quotation marks here because it's not, Askolkov did not conjecture that it's an equivalence. He conjectured that those two things are related. He didn't state in which way. There are some indications that this may be true. For example, it is known that if you take a polynomial sequence like j squared or j cubed, then it has the uniform distribution property. That, again, can be deduced from Weyl's criterion. And at the same time, Askolkov proved that polynomial sequences are not spectra of uniform convergence. There is also another indication which I want to mention, and that is, you know that sets, lacunary sets are Sidon sets, and in particular they are sets of uniform convergence, so somehow they have the strongest possible, they're the strongest possible spectra of uniform convergence. And it turns out that also they fail this property in the strongest possible way. There is a fairly recent paper by Peres and Schlag where they prove the following. They prove that for any lacunary sequence, there exists a theta so that this quantity here the norm stands for, the norm stands for the distance to the nearest integer. Okay. So the distance to the nearest integer is bounded below by epsilon over log epsilon. So they're not, these guys are not even just not uniformly distributed. They are not dense. Okay. They stay away from integers, for example, by this much. Okay. And this question has a very interesting history. So this question itself was posed by Erdős in 1976, and this is not a typo. It turns out that it was already answered in a paper of Hinchen much earlier. And Hinchen did not give a quantitative bound, but it can be traced from his proof, and it turns out to be much better than some of the other quantitative bounds that were proved much later. Okay, so and this is how this evolved. This question, well, it's interesting by itself, and the proof is also very interesting. It's actually a very nice paper. I think it's only less than 10 pages long. But it's connected to several different things. In particular, it's connected to some questions in graph theory, some questions in additive combinatorics. It's the method developed by Peres and Schlag turned out to be applicable to some questions in number theory, in particular Littlewood conjecture, the famous Littlewood conjecture about simultaneous Diophantine approximation. In particular, it was used several times to prove in negative results about getting close to this conjecture. But it also has some applications to Fourier analysis, again to lacunary Fourier series. For example, you can deduce from the Peres and Schlag result, you can deduce the following theorem. If you take a trigonometric polynomial with frequencies, well, a cosine polynomial with frequencies in your sequence, in your lacunary sequence, which is positive and is normalized to have value 1 and 0, then its integral, its its zero order term has to be large. It's at least this big. Okay, it's the same bound as in the Peres-Schlag theorem. Okay, and this is a direct relation. It's based on some prior work of Hugh Montgomery. There also seems to be an indirect relation to lacunary Fourier series, which, okay, maybe it's just indirect because I'm not smart enough to show that it's direct, or maybe it is indeed indirect. But if you look at the Peres-Schlag result, and if you recall Sedon's theorem, well, I'll just write it for a sine series now. And if you actually look at the proof of Sedon's theorem and trace the constant is, with respect to this epsilon, is going to behave in exactly the same way. And if you look at the two theorems, they seem very much alike, especially if you realize that this norm function, the distance to the nearest integer, it behaves pretty much in the same way as the sine. Well, okay, it's written here, so the sine behaves like this, and the distance to the nearest integer is like this. It's almost the same thing. So, well, there are some things that you can say immediately. For example, if I put this theorem with absolute values inside, would follow from Peres-Schlag theorem. Okay, or also if you have this Sedon's theorem, you can deduce some weak version of this statement. Whether these two statements somehow imply each other or not, that unfortunately I don't know. But there seems to be a clear connection. It is not known whether this log here is necessary. So actually, I talked to some number theorists who worked on related problems, and they say there are reasons to believe that it is. There are reasons to believe that it's not. So it's not quite clear. Okay. Well, okay, and the last thing that I want to mention. Okay, we came up upon this work. We came upon this work of Peres and Schlag when we worked on questions in discrepancy theory together with Jill Pfeiffer, Craig Spencer, and Xiaomin Ma. So, and by the way, again, this is still not checked, but I think together with Craig Spencer, we can give a different proof of the Peres-Schlag results. But again, with the same lower bound here, but with a different method. So the discrepancy questions that we considered were related to the following fact. The behavior of the discrepancy is strongly influenced by the geometry of the underlying objects. So far I talked about the discrepancy with respect to x as parallel rectangles, and we know this is what it behaves like. This is what I've been discussing. But turns out that if you allow certain rotational invariance or allow some curvature, then discrepancy behaves in a totally different way than its polynomial in n. Okay, so here there is a list of some results. Most proofs that I know, again, have to deal with Fourier analysis. You somehow use the fact that you would have decay of the Fourier transform of the characteristic function. Say in this case, you would use the characteristic function of the circles, and you would use the decay of the corresponding Bessel functions. Well, we asked the question, what happens in between? What happens if you, say, allow the rectangles to rotate, but just in some partial set of directions? And we came up with some answers in terms of the geometry of the rotation set, and in terms of the geometry of your set of directions, and basically in terms of its covariant function. So I don't state the results exactly. They will be a little technical. Oh, sorry, this is the picture of what I was just describing. This is what happens if all directions are fixed. This is what happens if you allow rotations or curvature. Okay, and so here I just list a sample of some consequences from our results. So if you allow things if you allow the rectangles to rotate in a lacunary set of directions, you still get logarithmic bounds, but you get a larger power of logarithm. And if you allow sets which are lacunary of order m, in particular sets of this type, for example, let me not go into the definition. There are peculiarities about the definition. You get this bound, which extends this one. Okay, if you allow if you take much thinner sets, so sequences like this, then you get very close to the bound that you get for a fixed direction. Okay. And well, if you take thicker sets, if you take sets with positive Minkowski dimension, then you actually get some polynomial growth here. Okay, so so these are the results that we have at the moment, and I will stop right here so that people can eat cake. Okay, thank you very much. So I think the one that I mentioned was in the beginning, sets with optimal L2 discrepancy. So in dimensions 3 and above, until quite recently, until about 5 years ago, all the constructions that were known were probabilistic. Okay? And then in 2007, I believe, Chen and Skriganov constructed sets with optimal L2 discrepancy deterministically, okay, without randomization. Actually, no. Yeah, that would be a very interesting thing to look at. I don't think anything. Off the top of my head, I don't know. I need to think about it. But well, I think well, it would make sense to consider it, and again, I would need to think if it would have applications or relations to other things. Probably. Yeah. No, it's not known. So even for Sidon, actually, there are not that many places. I think I saw a couple of references where this constant was actually traced. So first, I just computed it. And I was a little bit surprised at first, because at first I thought it should be epsilon. But then I realized that there is a little singular thing in the proof where you actually have to get that extra log with that proof. And then I did indeed see a couple other references where they traced the constant. It was epsilon over log epsilon. And I searched for it. I couldn't find anything better or any indication what it should be. So yeah, I think it's an open question. How does the Sidon constant behave when lacunarity approaches 1? Mm-hmm. 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 Well, for Hardy space, at least for the dyadic product Hardy space, things are pretty simple, because you can still use all the same proofs that you used for LP. You would just take the square function, and basically the same proof that I showed for L2 would work, because just instead of taking the Pythagorean theorem, you would use the square function, and the same proof would work. So HP would be very simple, yeah. At least that particular variation of HP.